Okay, welcome back to the course. In this session, we're going to deal with permutation tests for multivariate pattern analysis, but not only for MBPA, because I'm only evaluating a little bit on the general principles of permutation tests. Just to clarify before I start, my name is Joram Soch, and I'm working at the Bernstein Center for Computational Neuroscience in Berlin. I'm here reusing slides of my former colleague, Carsten Allefeld, who is now a lecturer at City University of London and who has given this talk in the previous years, so I'm representing him today. Okay, fine. When you're reading the words permutation test, you may be wondering, why should I use a permutation test? What's wrong with my significance tests that I'm performing? Well, the significance tests that we are running and also Bayesian analyses, for example, make certain assumptions about the distribution of the data, especially about the noise in the data. And sometimes precise distributions are not known, especially in multivariate pattern analysis. And here a permutation test makes weaker assumptions. It doesn't make no assumptions, but it makes weaker assumptions about the distributions than such parametric tests. Secondly, permutation tests provide ways for exact inference. That is, they are perfectly controlling the type 1 error rate, and if the null hypothesis is true, it is rejected at most 5% of the time if you have chosen your significance level to be 0.05. Finally, the principles of permutation testing apply in the exact same way to univariate and multivariate analyses, as you will see later in the talk. In this talk, I'm not going to provide recipes for standard data analysis contexts or for your everyday life fMRI data analysis, but I'm more trying to explain the basic principles underlying permutation tests, especially the concept of exchangeability. So let's just start with a simple example. Let's assume we have acquired this very little data set, which consists of two groups, A and B, and we have acquired 3 data points in each group, A and B. So the question that we want to address now is there a mean difference between groups A and B? Well, what we could do is just calculate the means of A and B and take the difference. That's the mean difference. That's our test statistic, and in this case, it would be 2. Now the question, of course, is how significant is that difference? Is that difference statistically significant? If there's no mean difference between the groups A and B, values can be exchanged between conditions, because this wouldn't change the distribution of the relative distribution of the conditions. For example, we could exchange the 7 with the 6 and the 1 with the 9. And exchanging data points within conditions means that we are permuting the data, which leads to permuted data. So we have an original data set and we have a permuted data set. Again, we are calculating the very same test statistic from the permuted data, and in this case, it would be minus 0.267. Of course, what we want to do in the end is to compute the test statistic for all permutations. In this very small data set, we are in the lucky situation of being able to actually evaluate all the permutations. So test statistics are calculated from all sets of permuted data, and test statistics are being sorted in descending order, which provides us a way of attaching ranks to those test statistics. The original dataset, also referred to as the neutral permutation because it's being left unchanged, is of course part of the set and also has a rank. The rank of the original value determines statistical significance. Sorry. So in this case, the mean difference would not be significant, because if you've chosen a significance level of 0.05, only the top 1 value in a list of 20 values would be deemed statistically significant. Equivalently, a p-value can be computed, which just happens by dividing the rank of the test statistic computed from the original data by the number of total permutations, which in this case would be 0.25, far from being statistically significant. One can also implement a test for decrease. So instead of asking, is there an increase from A to B, is there a decrease from A to B, which in the end would just mean to reverse the difference, or equivalently use the negative test statistic, also not significant in this case. Finally, we can also run a two-sided test where we use the absolute value of the test statistics, because in this way the most extreme negative values and the most extreme positive values are all becoming extreme positive values. So for this little data set, which is probably not very surprising, there's neither a significant effect of increase nor a significant effect of decrease. And this is also does not depend on whether we are running a one-sided or a two-sided permutation test. So from this introductory example, we are already able to derive something like a formal procedure for a permutation test. What is required for a permutation test is that a certain data set has been acquired or simulated, that a test statistic can be calculated from this data set and from permuted versions of this data set, that there is a significance level alpha below which you want to consider effects to be statistically significant, and that there is a set of possible exchanges between data points. I will come to that. I will come to what that means in detail a little bit later. So given that these requirements are met, the procedure is then as follows. First, we compute the test statistic T1 from the original data. Then we compute the test statistics Ti from all possible permutations, where I runs from 2 to the number of permutations. And this already signifies that I equals 1 is the neutral permutation corresponding to the original actually acquired dataset. In some cases, actually in a lot of cases, because this happens very fast, it's not possible to run all permutations. And in this case, one usually resorts to a random subset, randomly selected subset of the permutations, which is also called Monte Carlo sample. Next, we determine the rank of T1 within all test statistics Ti, which happens using this sum. So for each possible permutation, we're checking whether the test statistic Ti is larger than or equal to the test statistic computed from the original data. And if it is, we're adding up 1 to this sum, such that the whole sum would then give the rank of T1 within all the Ti's. Finally, we can calculate the p-value by dividing the rank by the number of total permutations. And if the p-value is smaller than or equal to the significance level, we reject the null hypothesis, accepting that there is a statistically significant effect. This test is exact, as I already hinted in the introduction, if alpha is a multiple of 1 over the number of permutations, and if there are no ties. Otherwise, the test is mildly conservative. Okay, in this formal procedure that I've just described, we have referred to a set of possible exchanges of data points. And this in turn refers to the concept of exchangeability. Formally, exchangeability can be understood as a situation in which we can exchange data points without changing the joint distribution of the entire dataset. This is perhaps best explained by looking at a few simple examples. So let's say we have just 2 data points or 2 random variables, x1 and x2, having this joint distribution. x1 and x2 are in this case independent from each other because there is no covariance between them. And they have the same marginal distribution, which means that they are independent samples from the same distribution, also called independent and identically distributed, which, by the way, is a special case of exchangeability. And independent samples from the same distribution can be exchanged. That is, if I'm here switching x1 and x2, the joint distribution stays the same. Independent samples from different distribution cannot be exchanged. So as you can see here, the mean of x2 is a little bit larger than the mean of x1, so that they don't have the same marginal distribution, which, if we switch x1 and x2 in this joint distribution, leads to a different joint distribution. Therefore, exchangeability does not hold. Please note that exchangeability refers to the null hypothesis. That is, if the null hypothesis is true, data points are exchangeable. On the other hand, if the null hypothesis is not true, exchangeability does not hold, because switching these two values does not preserve the joint distribution, as you can see when moving from here to here. Exchangeability can also be there if there is a dependency between variables, but this dependency has to be symmetric. For example, here we have a positive covariance between x1 and x2, but the marginal distributions of x1 and x2 are still the same. So exchangeability does hold and the joint distribution remains constant. Again, if there is a dependency, but this dependency is not symmetric because x2 has a larger mean than x1, the joint distribution changes when exchanging variables, and therefore this is not a case of exchangeability. You have to be very cautious because the null hypothesis may be wrong in rather unexpected ways. For example, this is the standard case of IID, independent and identically distributed data, which we have already looked at. But in the lower example here, x1 and x2 are independent from each other. They have the same mean, but they have different variance. And even though they x1 and x2 are independent from each other and have the same marginal mean, exchangeability does not hold because plausibly the joint distribution of x1 and x2 changes when they have different variances, and one is switching x1 and x2 here. So with these prerequisites, the formal procedure of a permutation test and the concept of exchangeability, we can now go and look at some basic test examples. The first one of this is the one which I've actually already used in the introduction. It's the univariate two-sample situation, where we assume that we have independent values sampled from two univariate distributions. And the null hypothesis is that the two samples come from the same distribution. In the independent and identically distributed, or IID case, values can be exchanged freely and arbitrarily between conditions. Upon exchanging those values, we would compute the difference of sample means, given by this formula, and this test statistic is sensitive to the difference in means, such that this procedure would be the permutation analog of the two-sample t-test. This can also be extended to a multivariate case, where we are now assuming that independent vectors, so vector-valued random variables, come from two multivariate distributions, and the null hypothesis, analogously, would be that the two samples come from the same multivariate distribution. In the IID case, vector values can again be exchanged freely, and after exchanging the values, we would train and test a classifier in a cross-validated fashion, which would give us a decoding accuracy as a test statistic. An example for this would be the classification of subject-specific patterns. For example, when comparing healthy controls with a patient cohort using structural MRI. And the individual entries of vectors would correspond to the structural MRI features, such as voxels or brain regions. Keep in mind that the entire vector is being exchanged between groups and not just individual or single values of this vector. There's a problem with accuracies, which is that sometimes decoding accuracies can only take very few possible values, because the number of possible values depends on the number of out-of-sample subjects or trials or runs being tested, and this can lead to ties, making permutation tests conservative. So now we're coming to a different situation. Again, we're considering two groups, A and B, but now we assume that two values from A and B are paired to each other in the sense that they are belonging to each other. So in this case, we would assume that paired values are sampled from two univariate distributions, and the null hypothesis would be that this is the same distribution. But now that there is a partial dependency, because these two values in a pair belong to each other, values can only be exchanged within pairs. We would then again compute the difference in sample means, and such that this is the permutation analog to the paired t-test. Here's the extension of this procedure to the multivariate situation, so the multivariate paired test. We would assume that paired vectors are sampled from two multivariate distributions. Again, because there's partial dependency, vectors can only be exchanged within pairs. We would train and test our classifier using cross-validation. And examples for this would be classification of condition-specific patterns across subjects, or classification of such patterns across runs within subject. So here, A and B are not two independent groups of people, but A and B might be experimental conditions. And because experimental condition is a repeated measure within subject, there's this partial dependency which prevents us from exchanging freely, but only allows us to exchange within pairs. If you are interested in an alternative to decoding accuracy, which is a very prevalent measure in machine learning based fMRI, you may have a look at this paper, which shows that multivariate samples can also be compared using significance tests. And this might actually be more powerful, because the test statistics in significance tests are not suffering from the problem of ties that accuracies are suffering from. These multivariate significance tests are not as well known as the univariate significance tests, but essentially they are based on the same principles of frequentist inference. So now I would like to point out some cases of limited exchangeability, that is, situations where exchangeability does not hold, or where exchangeability can only be applied in a very limited way. And a prime example for this is fMRI trials. So in an fMRI experiment, trials occur one after another, and there is a serial dependency in the functional MRI signal. So the first and the second are closely bound together, the second and the third and the fourth and the fifth, and so on, which can be visualized in this way. And because there is a serial dependency, exchanges of data points, like for example here, exchanging the data points denoted by A and B would completely disrupt this dependency structure as is shown on the lower visualization, which means that there is no exchangeability of values in fMRI time series. No matter if these are calculated on a scan-wise or a try-wise level. There is an exception to this, which consists in the following. So if these data points are attached to a try sequence, and this try sequence is itself randomized, what can be exchanged are, of course, the labels of the tries, because they are independent from each other from try to try. This, however, leads to a randomization test, which is not equivalent to a permutation test. So other than a permutation test, which makes assumptions about the distribution of the data, a randomization test makes assumptions about the distribution of the labels. So a disadvantage of this procedure would be that, strictly speaking, it only provides generalization to the space of all possible randomized designs, rather than generalization to the space of all data sets that could have been acquired. In some cases, there's a rather easy solution. So when an fMRI experiment is conducted in the form of separate runs or sessions, as it is becoming more and more common, then these runs or sessions can usually be considered to be independent from each other, and run-wise means or GLM estimates are often exchangeable, again, within runs, or within pairs if it's 2 runs. So in this case, run-wise classification may be a better alternative than running a randomization test. If you're looking to an alternative to classification in general, you may have a look at this paper, which describes cross-validated multivariate analysis of variance, which allows for arbitrary time series designs. So this may be more flexible than conventional decoding analyses, because the latter ones are usually restricted to very precise categorical classification contexts. Okay, in the end of my talk, I want to discuss further topics which may or may not come onto the table if you are performing permutation inference. And the first of these topics is the issue of multiple comparisons. So if you're analyzing brain data, you will inevitably run at some point several tests in parallel. For example, across fMRI voxels or across EEG channels. And this requires a control of the family-wise error, FWE. The FWE rate is defined as the probability of obtaining at least one false positive result from all the parallel tests you are running. And precise correction of the FWER depends on the dependency between tests, which in permutation testing is accounted for by using the same permutation across tests. So if you're choosing a random subset of all the possible permutations, it has to be the same in all the voxels or channels which you apply the analysis to. So let's say that Tij is the test statistic calculated from voxel J using permutation I. Then if you would like to test whether there's an effect somewhere in the brain, thereby rejecting what is usually called the omnibus null hypothesis or the global null hypothesis, you would use the maximum statistic. The maximum statistic is for each permutation the maximum across all voxels. And the omnibus p-value would then be given as the rank of the maximum statistic calculated from the original data within all maximum statistics calculated from the permuted data. divided by the number of total permutations. If, in contrast to that, you want to test whether there's an effect in voxel J, and this test should be corrected for multiple comparisons, then the p-value for voxel J would be given as the rank of the test statistic calculated from the non-permuted data in this voxel within the set of all maximum statistics, again divided by the number of total permutations. So the way we have described permutation tests so far, using our formal procedure and our definition of exchangeability, it can be seen that there are two core principles underlying this permutation inference idea. The first one is that you have to find a group of transformations under which the null distribution is invariant. This also includes the neutral permutation, the neutral transformation, leaving the dataset unchanged. Secondly, the test statistic has to be computed from the data after each transformation has been applied. And framed this way, permutation is just a special case of transformation, and exchangeability is just a special case of invariance. What I mean by group of transformations here is that the combination of two transformations is again another transformation. And permutation is actually a very nice example for this, because if you are combining two permutations, so permuting the data and then permuting it once again, you end up with another permutation. A very elegant example for this non-permutation based transformations is the non-parametric analog to the one sample t-test, which is called the sign flip test, because in the univariate, in the one sample t-test, there are no two samples between values can be exchanged. So the solution is instead to apply a sign flip to the data points, which again refers to the null hypothesis, because under the null hypothesis, the data are symmetric around zero, so that flipping the sign of your data points does not change the joint distribution of the data, which, however, is the case if the null hypothesis is not true. And this is exactly what we're trying to exploit in permutation tests. We want to see how extreme the exchangeability is violated in the original dataset compared with all possible permutations of the original dataset. A second example for a non-permutation based transformation that may be considered as a generalization of permutation tests is the so-called rotation transformation used in rotation tests. This is a link to an OHBM poster that my colleague Carsten once did on this topic. And the idea is that if you have spherical data, that is, if the errors are independent and identically distributed, you may not simply exchange x1 and x2, but you can also rotate the data, leading to the same joint distribution of the data. And as you can see here in the bottom example, if the null hypothesis is not true, then this rotation transformation does not preserve the joint distribution and therefore violates the generalized principle of exchangeability. Finally, this is a list of further reading. My colleague Carsten particularly recommends the first one, the paper by Ernst, Permutation Methods, a Basis for Exact Inference. With that, I would like to thank you and hopefully see you again next year. Bye-bye.
Welcome to the educational course Machine Learning for NeuroImaging. And this is the annual meeting OHBM 2020. Today, I will talk about how do we test our hypothesis, a Bayesian approach. I'm Emanuele Olivetti from the Neuroinformatics Lab of Fondazione Bruno Kessler and Center for Mind and Brain Sciences in Trento, Italy. So, to motivate a bit the content of this course, I'll tell you this one. Can we decode faces? So images of faces or scrambled faces are shown to a subject during a recording session in a MEG device or in an MR device. These images, of course, they are very different. In one, there is a face, there is a content, semantic content. In the other one, it's just a scrambled face with basic low-level features, which are very similar to the face, but it's not. And we are interested in decoding faces. So once we have recorded multiple presentations of the stimuli in a randomized way, we want to set up a classifier on the image data in order to decode, to predict what was the stimulus presented to the subjects while recording the brain activity. So how do we do this? We need to do hypothesis testing, and we start with scientific questions like, is there information about certain mental process like face processing within brain data? And then we, in order to answer this question, we may set up two hypotheses, two competing hypotheses. Yes, there is information. No, there is no information. And another question like this one is it possible to decode stimuli from brain data? Okay, one hypothesis, yes, decoding works, we can decode, or no decoding, it does not work. And going even more in detail, which is closer to the analysis we will do, can my classifier discriminate the category of the stimulus? Yes, it can, not it cannot. So in the end, we have some hypotheses from our scientific questions, and we want to test them using some framework, some statistical framework to do that. So this course is about testing hypotheses. I will start talking about the classical frequentist, let's say, framework or way to do hypothesis testing. And there are basically two frameworks here, the significant testing and hypothesis testing. And then I will move to the Bayesian one, Bayesian hypothesis testing framework. And why do I start with the classical to the frequentist one? I expect that most of the people attending this course are familiar with that, or to some degree. But there is also usually a bit of confusion between the two different frameworks, the significance testing and the hypothesis testing. So I want to clarify a bit. In introducing these concepts, then it's easier to talk about the Bayesian hypothesis testing framework as a comparison. So it's more clear. So let me start. So first of all, when we do hypothesis testing, there are two different ways, two different paradigms to face the problem. One is the classical one, also called frequentist, which was proposed by Ronald Fisher on the one side and Josie Nyman and Egon Pearson on the other side. Then, let's say from a completely different point of view of the Bayesian statistic, there is Harold Jeffreys that propose another framework to do hypothesis testing. Okay, here on the right side, on the bottom right side, you can see there is also Frankenstein. That's because, unfortunately, over the decades, the classical framework has been, let's say, abused or used in the wrong way. So many practitioners just use the two frameworks together, a mix of them, in what is called the anonymous hybrid in the literature. So a sort of mix of two things, which unfortunately does not work. And that's why I represented it as a Frankenstein. So let me start with the first one. So Ronald Fisher was the first one, was a very famous statistician, was the first one to define a framework for testing the hypothesis. It's called significance testing. The principle that he used is that of inductive inference. So you collect a sample of data, and from the sample, you want to know something about the population. The Fisher's recipe to do significance testing, to test hypothesis, is the following. First of all, you have to set up a null hypothesis. That's the one that you want to disprove with the experiment, that basically there is no effect in your data. And the second step, you have to choose a way to summarize your data into a number. This is called a test statistic, which, like the t-test, it's the t, or it could be the average. Or here we are talking about decoding. It's like the accuracy of the classifier or the number of correct prediction of your classifier. But we will see that in a minute with an example. And in step 3, you have to derive what is called the null distribution of this test statistic. Basically, once you assume that the null hypothesis is true, you want to know how the test statistic is distributed. This can be done analytically using math or by resampling. And you might be familiar with a technique like the permutation test, in which you do permutation to create a null distribution. Then, after that, you have the null hypothesis, the test statistic, the null distribution. You can execute your experiment, collect the data, and compute the actual value of your test statistics, the observed one. At this point, the Fisher recipe ends when you report the p-value that you obtain from your data, or from your observed test statistic, which is the probability of obtaining such test statistic, the observed values, or a more extreme value, under the hypothesis that the null hypothesis is true. And this is a measure of evidence against your null hypothesis. Okay, this is a little bit abstract. Let me show you an example. So it's about classifiers. In this one, in this example, this is a leading example that I will use throughout the course. We have a classifier that is trained on some data, the MG data that you have seen at the beginning. And at this point, we test the classifier over some test data. And we assume to have a test set of size 40, like the subject was presented 40 times in a randomized way with the stimulus of phase and scrambled phase. And at that point, these 40 are used just to test the classifier that has been previously trained in some way on some data. So the null hypothesis that the classifier predicts at chance level, so at random. The test statistic in this case and throughout all the presentation is the number of correct predictions, C. And we have to remember it's a number between 0 and 40. So if the classifier is perfectly correct, it will predict correctly, whether it is phase or scrambled phase, 40 times over 40. Or if it is just predicts a chance level, like in the case of the null hypothesis, it will predict like on average 20 times or more or less, but according to which distribution? The null distribution in this simple case is known to be the binomial distribution, which is depicted here on the right side. So as you can see, in this case, 20 is the case in which there is the higher probability, because of course, predicting by chance 40 times, you have 20 correct prediction on average, it's the more likely result. But of course, you can have more prediction or less prediction according to the distribution that are just less likely, as the graph shows. Then we run our experiment, and let's say that we observe 40 correct predictions by our classifier. So what is the p-value? The p-value is the probability, according to the null distribution, of obtaining the 28 or more correct predictions. So we sum up all the values from 28 to 40. So basically 28 is here where there is the triangle, and we sum up all these tiny values of the tail of the distribution till 40. And if we do that, we get 0.008, a very low number. So how do we interpret, how Fisher told us to interpret this value? So first of all, a low p-value means that the null hypothesis that our classifier predicts at chance may not be a good model. And in this case, we reject the null hypothesis. And if the null hypothesis is rejected, remember, according to this framework, that nothing is said about what should be accepted. So we just know that we should reject the null hypothesis, just one hypothesis. Moreover, this is just a quote from the famous book of Fisher, Statistical Methods for Research Workers of the 58. He said, personally, the writer is Ronald Fisher, prefers to set a low standard of significance at the 5% point. So Frequently, you are familiar with this 5% threshold for significance, but this is just a personal choice of feature. There is no theory behind that. You have to remember that in this case, what you report is the p-value, not that the p-value is below a certain threshold. Okay, let's move on to the second, let's say, the second framework of classical frequentist statistic for hypothesis testing. This was designed by Jerzy Neyman and Egon Pearson more or less at the same time in which Ronald Fisher proposed his significance testing framework. This is called hypothesis testing framework. And the principle is different, is that of inductive behavior. So you adjust your behavior under limited information. What is the recipe of Neyman-Pearson? First of all, you have to set up two complementary hypotheses, so not just one. This is a major difference with the other framework. The null hypothesis and the alternative hypothesis, H0 and H1, are the two complementary hypotheses. Then, as a second step, you choose, as before, a way to summarize your data into a number, the test statistic. Then, step 3, you have to derive or to obtain the null distribution, so the probability of the test statistic when the null hypothesis is true, but also the alternative distribution, the probability of the test statistic given H1. And now, step 4, in my opinion, is the most important step of this framework. You have to decide the false discovery rate, so the probability of being wrong at the end of using this framework, of rejecting the null hypothesis when the null hypothesis is true, so claiming that you have made a discovery when there is no discovery. So you have to decide the level at which you accept that, and you, of course, want the lowest possible. Once you decide this number, then you have to decide also the sample size, so how much data can you collect. This is, of course, constrained by, I don't know, the resources, the time, the money that you have, the amount of time that by law you can keep the subject in the scanner for your experiment. And so this is a number you can control in some way. Once you decide alpha and n, you basically can compute beta, given the null distribution and alternative distribution. The beta is the probability of rejecting the alternative hypothesis when it is true. Of course, these three numbers are linked together, are constrained one by another, so you can decide two and obtain the third. Usually, we decide alpha, we are constrained by resources to n, and at that point, we compute beta. In a second, I will show you one example. At this point, with the distribution and these levels, we can compute what are called the rejection regions. So these are, let's say, intervals of the test statistic for which you reject the null hypothesis and accept the alternative hypothesis, or vice versa. It depends on which region you are. At this point, you run the experiment, compute the observed test statistic as before, and then what you do, you compare your observed test statistic with the rejection regions and reject the null hypothesis and accept the alternative if you are in a rejection region, or vice versa. But let's see this into one example. So the example is the one as the one before. We have, again, our classifier. There are two hypotheses. The first one is that the classifier predicts at chance level. The alternative hypothesis is that the classifier predicts better than chance level. And the test statistic is again the number of correct predictions, C. And the null distribution is again the binomial distribution. We have again 40 a test set of 40 samples, of 40 presentations of stimuli to the subjects. And since this is then the null distribution, the probability of being correct in the prediction is 0.5. And the null distribution is depicted here, is the same one as we have seen in the graph before in the Fisher approach. Alternatively, we have the alternative hypothesis, H1. Here again, the distribution, its distribution is the binomial distribution, but in this case, we have to decide what is the probability of being correct. In this case, of course, more than 0.5, because we said that under this hypothesis, the classifier predicts better than chance level. What number do we choose? Here is either a choice that we do knowing something about the problem, or we have some left out data that we are not using and we estimate a bit that number. On this part, let's say this paradigm is not entirely easy. Anyway, I put 0.7 and I have the second distribution. At this point, if we move it along the graph, we can choose a threshold for which we decide how much is alpha, so the number, the frequency of fault discovery, the number of mistakes of let's say, a rejection of the null hypothesis that we do mistakenly, so claiming discovery when there is not, and given that n is fixed, we have we just obtain what is beta, so the probability of rejecting the alternative hypothesis when this is true. So basically, we move into this graph, and we can decide which level do we want of alpha, and then, of course, accept the one of beta. In this case, we want less than 5%. It's just a choice for in this moment, less than 5% of false discovery rate. So the rejection region is when the number of correct prediction is equal or greater than 26. At this point, we ran the experiments. We know that in these experiments, we got 28 out of 40 correct prediction, and so this is greater than 26. The null hypothesis is rejected, but we don't just report that. We also report that alpha was 4%, beta was 20%, and the power, you may have heard about this term power, the power of the test is 1 minus beta is 80%. It's like the sensitivity to discovery of my experiment. Okay, these are the two framework, significant testing and hypothesis testing. Unfortunately, from the 50s on, they were mixed frequently in the literature. You can find so many articles, even today, as that's very sad. And so that this mix is wrong on many levels. So I don't want to go into the details of this one because I don't want to teach wrong. But basically, in this framework, which is a mix of the two, you decide alpha, but then there is no beta. You reject the null hypothesis and don't specify the alternative, but you say that you accept the alternative hypothesis. So there are a number of wrong steps, and they should be avoided. That's why you need to be conscious of that and to avoid to mixing the two frameworks. You have just to choose one among them. Or better, you should move to the Bayesian hypothesis testing, which is the main topic of this course. Now that I introduced so many concepts, it's easy and quick to talk about Bayesian hypothesis testing that was proposed by Harold Jeffreys, more or less along the same years of the other two frameworks, but this was not so famous at the time, and even today is not, let's say, prevalent. Anyway, what is the recipe of Bayesian hypothesis testing? So in this framework, you have to set up 2 or more mutually exclusive hypotheses, H1, H2, H3, H4, depends on your problem. If you have multiple hypotheses, you can deal with them. Only one with Fisher, 2 with Ninon and Pearson, and as many as you want, but at least 2 in the Bayesian one. Then you have to quantify the prior probabilities of each hypothesis. What is this? This is just a number, a probability that from your current knowledge, like the current literature or what you know about the scientific problem you're dealing with, you can associate to each hypothesis. Like, can we decode phases and from scrambled phases? There are 2 hypotheses. Yes, we can. No, we cannot. And what is the probability of each of them? So I could say it's 50-50, but maybe if I dig into the literature, I see that it's sort of frequent to decode them. So maybe it's 80-20 or 20-80. So here, and this is something characteristic of the Bayesian hypothesis testing and the Bayesian framework in general, I have to quantify my current knowledge before collecting the data, or the degree of ignorance I have in before collecting the data. And this is exactly the step. Let's say 50-50. Anyway, the third step, it's to model the likelihood of the data. This is the probability of observing certain data under one hypothesis and the other hypothesis, or each hypothesis. This is sort of similar to what we have seen before in the other two frameworks, but it's then in practice it's different. You will see in the example. At this point, you run the experiment, collect the data, and with that, you can compute the posterior probability of the hypothesis. So initially, I had a prior probability, and then I have the data likelihood, so the probability of the data given each hypothesis. Here, I compute the probability of each hypothesis given the data. So after seeing the data, what is the relationship between these quantities? It's here in the formula. This is a Bayes theorem or Bayes formula. And it looks an easy formula, but of course there is some, let's say, mathematical difficulty, because especially in step 3 and in this step 5, it's not always straightforward to do this computation. Usually it can be also a bit demanding, and in a minute I will show an example of that. Anyway, once we compute the probability of each hypothesis after seeing the data with this formula here, we can just report the posterior probabilities, or the ratio between them, which is called Bayes factor, that I don't cover here unless there are questions in the question time. Okay, the example. Again, the same example. We have two hypotheses. The first one is that the classifier predicts at chance level, and the second one is that the classifier predicts better than chance level. Okay, as I said before, I need to define a prior probability of each hypothesis. This time, let's say it's 50-50. I don't know which of the two hypotheses is prevalent, so I would say before seeing the data, for me it's 50-50. And now the data likelihoods. As we have seen in previous examples, the probability of observing a certain number of correct predictions in 40, let's say in 40 repetition, or in a test set of 40, when predicting at chance level, it's the binomial distribution with these parameters here. Differently, when we are under hypothesis 2, that the classifier predicts better than chance level, again, the probability of observing a certain number of correct prediction is binomial, but the frequency or the probability of being correct is not 0.5, but it's something between 0.5 and 1. That is why this model has a second level in which the probability of this parameter is between 0.5 and 1. And here I have decided that given what I know of this problem, there is uniform probability that it can be whatever number between 0.5 and 1. So this is the model of the data likelihood. It's a bit more sophisticated to what we have seen before, and it's enough for computing the posterior probability, because at this point we run the experiment, get the data, and observe 28 correct predictions, as we have seen in the previous examples. At this point, we apply the formula and compute the posterior probability, that in this case are around 5% for the first hypothesis and 95% for the second hypothesis. So what we can say is that there is 20 times more probability that our classifier predicts better than chance level than the classifier predicting at chance level. Of course, here I've skipped some steps because the computation does not appear. So let's spend a few minutes just to understand how to compute these posterior probabilities and apply the formula that a couple of slides ago were there. So we need some ingredients. First of all, look down here. This was the formula to compute the posterior probability. And as you can see, there is one for the first hypothesis and one for the second hypothesis. So the elements that we need in order to compute this formula are the prior probability, you may remember, 50% for one hypothesis, 50% for the other hypothesis, and the data likelihood. But this time, of course, computed with the observation, with the data that we collected from the experiment, the 28 correct predictions. So in case of hypothesis 1, the data likelihood, the probability of the data given H1, is the binomial distribution where we plug the numbers 28, 40, and 0.5, and we obtain 0.005. This is the data likelihood under that hypothesis. It's a bit more complicated to compute the data likelihood under the second hypothesis, that the classifier predicts better than chance level. In this case, we have to integrate the binomial distribution where all possible values of the parameter pi that is taken uniformly from 0.5 to 1. How do we do this? Usually we can do it, let's say, in two ways, analytically, or we can do it via Monte Carlo. In this case, let's do it with Monte Carlo, and we obtain 0.097. With this number, 0.097, 0.005, 0.5, and 0.5, we plug it into the formula of the posterior probability, and we obtain our 95% probability for hypothesis 2, which is 20 times more likely than the 5% of the posterior probability of hypothesis 1. Now, just to clarify a bit, what does it mean Monte Carlo here? It means something very simple. So we can approximate the integral by basically as a summation, by a summation, or just averaging values. We draw, let's say, some thousand of random value from this uniform distribution, plug into the binomial, and average this quantity. In Python code, for example, this is just a few lines. So we loop 10,000 times. In each iteration, we draw from a uniform distribution from 0.5 to 1, the value pi. We plug it into the binomial probability distribution and probability mass function and obtain the value here. And then we basically just average that. There is a term here because this is related to the uniform distribution, which is between 0.5 and 1. So there is this extra term. But basically, with 4 lines of code and a few seconds of computation, we can compute this 0.097 and obtain the result. So let me now wrap up a bit the take-home message of this short course. There is more than one way to test hypotheses, and learning about these different frameworks is very interesting. So significant testing framework, hypothesis testing framework, Bayesian hypothesis testing framework. You can read about them there is literature, very interesting literature, and I have many articles about this topic in the references that I invite you to read. And so in the end, which hypothesis testing framework should I use? It's a long debate. So the first, let's say, there is consensus that you should just use one properly or all of them in order to see whether there is some, let's say, converging evidence. And in my opinion, you should use the Bayesian one because it can represent better many situations that we have in our experiments. And once you learn it, it's very straightforward and clear to understand. With this, I thank you for following this educational course. And if you have questions, we can catch up in the question time. Thanks again.
Hello. Here is Bertrand Thirion. I'm going to discuss in this presentation how we make a good model for multivariate brain activity decoding. So I'll try to give some practical hints for that. First, I should define what I mean with decoding. So here I do a reference to the standard processing analysis framework where you acquire data to check a certain neuroimaging or neuroscience theory and organize them in an experimental protocol. And then once you have collected your data, you want to compare statistically the image that you have acquired with the behavior of the subjects during the experiment or the stimuli that were presented. So here, decoding means predicting the behavior from images. It's a converse operation of encoding where you analyze the converse mapping. But in a broader sense, we can also think of decoding as predicting something about the subject, like in population studies, where you would like to study some characteristics of some populations, and so do some individualized prediction on the participants. So this also falls under the decoding idea. At least formally, it's a very similar problem. In this presentation, I will try to give you 2 main advices. The first one is to keep your decoding model simple. And the second one will be to beware accuracy and significance. I will make that clear. And then I will show you some recent developments about the inference approach to decoding in fMRI. So let's start with keeping the decoding model simple. Well, in all research activity, I think it's important to be always be able to explain what you do clearly in plain words, like for the general public. So you should be able to explain what your predictive model is actually predicting, how it's working, and how you are evaluating it. How do you believe that this model is good? I'm saying that because as a reviewer, I quite often see some contributions where it's very hard to figure out what was done and why, and what is what the model is doing exactly. Then we might have to define what simple means. Let me start with examples. If you think of the decoder itself, I would say that arguably linear models are quite simple in general. I would say that classification trees are somewhat simple, depends on the structure of the tree. Kernel methods are not so simple because you need to explain what the kernel is doing and how it acts on data. And I would say that deep learning is not simple at all because it involves lots of parameters, a layered structure, which is hard to figure out and to interpret. But of course, simplicity goes beyond that. And I think it's about the whole procedure that you use. And it can involve, for instance, feature selection, the way you select parts of the brain domain for your classification task, or the way you tune the parameters if there are many free parameters to tune. So in that framework, I think it makes sense to define simplicity as having few steps and few parameters to tune. Why should we have only few parameters to tune? Because parameters tuning is hard. It's especially based on limited data, and the more parameters you will have to tune, the more issues you will encounter, and the less reproducible your analysis will be. Yeah, I'm just taking an example from the Ninon library, where we try to set, we study a parameter, which is the number of voxels used in the decoding model. So it's very easy to interpret. It goes from 10 to 5,000. And then we study with the cross-validation on some data how well these different values perform, and this gives a blue curve. And then we try on left-out data, completely different data, to see what score we obtain. And you see a big difference. Maybe 10% in accuracy are lost between the two cases. And this is just random fluctuations, just due to the limited data, possibly some shifts in the data between the two. And this tells you that just taking the blue curve to set the parameter of the model might not give you a very good way to do it. So, and of course, the recommended way to do it is to have a nested cross-validation loop in which for each fold of the analysis, you retrain internally the choice of the parameter to have the best possible model at each iteration. And this gives you a fixed value of accuracy, which is probably the best choice. But so when you see how strongly the things can vary, you see the difficulty, I think, of the problem. So again, what is a simple model? If you take two linear models, there is not one linear model that can decode your data. There are many, and you need to choose among them. For instance, here I give an example of a linear model that has a few blobs, so it's at least easy to interpret, and it seems pretty stable. You can check a bit the data, the model will be almost the same. While this linear model, it works as well as the first one, but has a much more complicated landscape, and so potentially harder to reproduce and less stable. It's actually the case, we have shown this, and it's typically a case where we have used Bootstrap to stabilize the model and provide clearer maps. So we provide, now there exists technique that improve the robustness and maybe the simplicity of the model. And then there are lots of good news. for brain imaging. The first one is that simple models, so like linear models in particular, work well on brain imaging problems. Here I'm giving an example where it's the question is to predict some individual characteristics based on connectome data. And we compare many different classifiers on many different data sets. So it's a pretty comprehensive comparison. And what we see overall is that the best methods are the linear methods, those that just predict linearly the outcome from the data. And it's well, it's good news because you don't have to go to all these fancy, complicated techniques. In a different setting, it has been reported that for more complex models, kernel-rich regression would do as well or better than deep learning. So again, you always have this trend that rather simpler models perform as well or better than complex models. Second thing which makes your life easier is that I said that parameter tuning is hard, it's difficult, but now we have libraries that essentially do it for you. For instance, here I take the example of ridge regression in scikit-learn. If you take the ridge CV estimator, it will learn the parameters internally without you having to take care of that. So you just need to provide a grid of parameters at the beginning, and the model will take care of that. It will do the nested cross-validation, and you don't need to worry about that. And the third good news is that now we even have more practical estimators, like the decoder objects that has been made available in Ninon recently, in which you simply have to specify a model. So you specify a classifier model, a cross-validation scheme, a mask. So what region of the brain do you want to work on, and the scoring function. Then you just input data and you get an accuracy score. So now we are in this phase where all these steps are well understood and we can create high-level objects to make this easy to use. There's just a little thing I would like to say on the interpretation of linear models. I highly recommend linear models, but beware the interpretation. Indeed, in many papers, you can see that since we can decode some information like face identity linearly from brain images, well, this brain identity feature, these face identity features should be encoded linearly in the data. And this is not true. You can perfectly decode linearly some information that is not encoded linearly in the brain data. I take a very simple example on the case of vision. So assume that you have a one-dimensional visual field, and so the information of interest is the position of the object. It's the abscissa of the object along this axis. And then we have neurons with a receptive field that are aware of the that activate when the object reaches this receptive field. For instance, put an object here, these neurons will activate. Now, if you put the weights that I drew here in pink on the neurons, you can decode the information of the neurons, which is estimate the position, the abscissa of the object, given the neuron's activity, just by linearly summing the activity of the neurons. I take another example here. If you change the position of the object, these neurons will activate, and just by these weights, you will be able to predict very accurately the position of the object. Now, none of the neuron encodes linearly the position of X, the X information, but you can decode it linearly from the data. So do not interpret linear decoding as a linear encoding. That's a different thing. Now, I would like to switch to the second part of the presentation. So beware about accuracy and significance. So a very important step once you have defined and run your model on data is to get the level of accuracy. And you might be in the situation where you get like just kind of borderline accuracy. If chance level is 50%, you can get like maybe 55%. And this is problematic for 3 reasons. First one is that error bars are large. You say 55% accuracy in average, but how much variability is there around this 55%? Is it really different from 50%? Second point is that the model may have picked any confound in the data that helps predicting. For instance, the model may not be sensitive to the nature of the object that is presented, but simply like to some low-level features like color, and not everything is pretty exactly equal. So when you're just close to chance, it may be that the model just picked some features of the data and does not decode what you want it to decode from the data. And finally, it's more the question of statistical significance versus practical significance. Maybe the 55% accuracy is significant, but yet, is it useful? I mean, if we're just borderline at prediction, maybe we don't really get the information. If you want to predict, I don't know, a disease status, you just want to be just borderline. It's not a useful diagnosis. So for it to be useful, you need to have some decent accuracy, maybe close to 80, 90%, or even better. So this is practical significance, and this matters, of course. So let me now go a bit more into details about that. The first point is about the uncertainty in accuracy, and it's just related to the limited data that you work on. So we have performed a simulation where we measure prediction accuracy for different dataset size and different consolidation schemes. I don't go much into details, but just see the numbers. With 30 samples in your dataset, your uncertainty about the final score will be about 15%. And if you increase the sample size to 100, it goes down to 10%, and to 1,000, it goes to 2-3%. So the more data, the better. And that's plain statistics. And of course, you should keep a significant amount of data in the test set and rather avoid using leave-one-out cross-validation. Although leave-one-out cross-validation is not wrong, it's just suboptimal and costly. Second point is that these were just based on numeric simulations, but if you do that on neuroimaging data, fMRI or MEG or anything, you exactly find this type of numbers. So even with relatively important sample sizes, you can get very large uncertainties in the accuracy scores, just because there's lots of variability in the data that come into play. I think it's always important to emphasize the importance of large sample sizes. So here, let's take a very simple, very easy problem, which is to predict age of a person from VBM data, so gray matter density maps. You can predict almost perfectly the age information, with 80% of the information being predicted if you have a large sample size, like in OASIS. So here with 100 subjects, we are close to 80% accuracy. But of course, this degrades when you decrease the sample size. With only 10, 20, or even 50 subjects, you don't have such a high accuracy. And also more spread in the accuracy values you obtain across cross-validation folds. But there's even worse, if I can say, which is that if you use a linear classifier, and probably you should use a linear classifier to do this kind of prediction, then you will want to interpret the pattern map that predicts age, and why not? The question is, if you take small groups of subjects, maybe 10 subjects, you will have a certain pattern map. Okay, great. Now your colleague does that on another group of subjects, and he gets another map. Which one is right? Well, they're pretty different, actually. And if you do that in different samples in the population, like in 10 different groups, you end up with 10 different maps, and it's very hard to say just from that what are the relevant regions and whether you can even trust any of these maps. So now let me just make this a bit quantitative to make my point clear. So based on these maps obtained from different groups, well, why not simply average those, like in a meta-analysis, if you like? So you will have the average predictive pattern of age across these groups. And you can also take the variance of these patterns, and so which gives you these two maps. And then what you can do is simply summarize them with a Quantz-D statistic that shows you the effect size of the age effect on the gray matter maps using the classifiers. And you obtain this. So here all the values are pretty close to 0. So we have a pretty weak effect. So it's hard to draw a conclusion from this data. And of course, now it was with 10 subjects, but if you do that with a group of 20, 50, 100 subjects, now the map becomes gets much larger values. And so it works much better. You've got much more evidence from the data. So your interpretation of the pattern map is much clearer, much easier. Another point that I would like to make is that you may wonder when you get an accuracy score whether it's better than chance. Because sometimes you have several classes and they are not balanced. You have got more samples in a class than in another, so chance level is no longer 50%. And you may have to calibrate, essentially, what is the chance level for this experiment. So we have some tools to do that. If you take from scikit-learn a dummy classifier, it's just a classifier that will give as an answer the most frequent class in the training set. So it will give you what a stupid classifier would do, and it's very easy to get a baseline with this classifier. Or you can even get a permutation test score that uses internal permutations. And then the way to describe your result will be on different folds of the data. You are doing better than chance or better than permuted in maybe 80%, 90%, or 100% of the folds. And then you can have some indication of the significance of your finding, how much better than chance you are. One thing that you should avoid is to take the accuracy scores across cross-validation folds and run like a one sample test, a student test on these scores. Why not? It's because these scores are not independent. It's a cross-validation. All the data are used each time, but either as training or testing. But so the scores are not independent. So you can compute a student statistic, but you cannot interpret the statistic as a p-value. If you find a t of 3, it doesn't mean that the p-value is, I don't know, 10 to the minus 3, for instance, because this would assume independence, which is not there. So this one sample test and accuracies, I think, should be avoided. Finally, I would like to draw your attention on some recent developments on the inference on the multivariate decoding models parameters. Indeed, when you use linear classifiers or linear predictors, as I told you, you've got an explicit coefficient maps or weight maps that tells you how strongly different brain regions are involved in the classification. Or it's a weight that tells you how much each voxel, each location in the brain contributes to the decision. And of course, then you may wonder, oh, this voxel here in yellow, does it mean that this is the most predictive one? Does this one encode the face information? If this was a face versus other object classes classifier, for instance. And so the answer is not straightforward, because what predicted the outcome, whether the subject was viewing a face or not, was not that particular voxel. It's the whole brain map. So you cannot separate this voxel from all the context. And so the interpretation is not straightforward. Actually, if you conceptualize a bit more this, the way, I think the proper way to think of that the multivariate maps has information in different voxels. So I call X1 the information in the voxel 1, X2 in voxel 2, and so on, until the P voxel. But there are thousands of them. And then these voxels are used to predict some information like behavioral or personal information of the subjects. Why? These voxels are interacting, of course, they are connected somehow. And the question is, can we say that whether the voxel I has some impact on Y? This is the key question. So in the most basic formulation, you can frame this as a conditional correlation test, where you try to assess the correlation between xi and y, the output variable, but given all the other variables. Or more generally, a conditional association test where you have some statistic and you try to measure whether xi has some relationship to y, but once you have removed the influence of all other variables. And of course, this score depends on all the brain. So it's not straightforward. Actually, we can draw a parallel with the standard linear models that you could also use. That would simply compute the correlation between xi and y. It would be the marginal correlation, which is easy to compute, but unaware of all the context. And here with the multivariate linear models, you have these conditional correlations, which are much harder to compute because you have to condition on all the other brain regions. So computing them is an ill-posed inverse problem, but now can tell you whether region I has a specific information about Y. And actually, if you want to make a good inference about the involvement of brain regions into cognitive processes, you probably should use both. This was very clearly explained in this NeuroImaging paper, which I refer you to. Now, the problem is that for the conditional correlation to be computed, you've got this ill-posed inverse problem to solve. Ill-posed inverse problem, this means that even for linear model, there are an infinite number of possible solutions to it. So at the end, the actual solution of your algorithm will depend on the priors put by your algorithm on the solution. And we can design lots of different priors. And depending on the prior used, the solution will look completely different. Here, for the same problem, the same data, I provide 7 different solutions. More or less, the 7 solutions have the same accuracy. So they all work well. They are all valid solutions to the predictive problem. But of course, they produce completely different brain maps. And so you might not draw the same conclusion on the importance of a certain voxel, depending on the methods you used. So it's maybe a bit bad news. At least it tells you that you should be aware that your model has priors and that the solution looks like the priors you used to estimate it. How to go further? Well, what we have been proposing recently was to say, now with multivariate models, we can actually estimate these conditional associations and the variance around it. So take the problem as the one of estimating the conditional association of a certain voxel with the target Y, conditional to all other regions. But we will get this effect and the uncertainty about it. And so now with this uncertainty computation, we can say whether the region I has indeed an effect or not with a traditional frequentist analysis. And so, of course, in terms of implementation, it's a somewhat more complicated thing that uses internally some clustering to simplify the problem. But this gives a so-called Encludel method, which we have developed recently, that estimates jointly the predictive pattern and its variance. So this can be used to provide p-value on the pattern maps and then control type 1 errors on the detection. This model has good phase validity. We can, for instance, use it on the HCP dataset across subjects. For the gambling task, for instance, it will I think, find a good pattern to distinguish the loss or the gain in the gambling. In the emotional data set, it provides a fair pattern for distinguishes face versus shape outlines, or in a different data set to distinguish between attending to sentences versus list of items. And these patterns can be error controlled with a family-wise error rate control. Last words on interpretation. Always remember that when you show a discriminative pattern, you should always be very explicit about what it's discriminating. So if you try to predict whether the subject is viewing a face or a house, it's different from predicting whether the subject is viewing a face versus a house or versus a tool, a body part, a checkerboard, a word, or anything like that. So you will end up with different classification models, and so potentially different interpretation. And of course, you should always be explicit on whether the classifier procedure is 1 versus 1 for each pair of category, 1 category versus all possible others, or 1 category versus rest, for instance. And this is very important for interpretation. So it's time to conclude now. So my 2 main messages in this presentation were to limit the complexity of decoding procedures, because complexity comes with major costs and time and statistical power. The good news is that linear models perform well, so we can rely on these simple models, which is great. And we can also use high-level objects to make this easy. Second point is that pattern maps are hard to interpret. Because they are relative to many choices. I think I illustrated that clearly. In the theoretically, at least, they measure some conditional associations between the outcome and the features, so the brain activity. But we are now developing novel estimators, a second generation of estimators that come with statistical guarantees. To finish, a word on software. I based my examples on the Ninon library, which provides now a high-level API to deal with all these issues and lots of examples. So I think it's a good start point to work on this, provided you want to use Python. With this, I would like to acknowledge the contribution of my coworkers from the team and some colleagues also. And finally, I would like to refer to some bibliography. These papers I think are very interesting to read if you are interested in these topics and want to go further. I haven't covered them in this presentation, but I really encourage you to take a deeper look at them. Thank you.
Hi, my name is Valeria, and I'm a postdoc at the National University of Singapore with Thomas Yeo. And today I'll be talking about unsupervised approaches and how they can be useful, especially when you have undefined labels. So I'll start by explaining the differences between supervised and unsupervised approaches and how they actually answer to different questions. Then I will go into one specific approach called partial least squares. I'll explain how it works, how we test and interpret a PLS model, and I will illustrate this approach with an example of brain behavior associations linking functional connectivity with behavioral data in a clinical data set. And finally, I will explain how PLS compares with other similar unsupervised techniques such as PCA or CSTA. So a classical example in machine learning is you have pictures of cats and dogs, and each of these pictures is labeled as being either a cat or a dog. In a supervised approach, we aim to predict the label of a new picture. In unsupervised learning, you don't have any labels to start with, and what you want is to find some sort of hidden structure in your data, maybe come up with new groups. For example, depending on your features, your approach could result in having one group of animals with floppy ears and another one with pointy ears, or a dimension like a color spectrum spanning from brown to gray, with each animal having a loading of this color dimension. So when is unsupervised learning useful? Well, when you can't use a supervised approach because your labels are not reliable. For example, in psychiatry, we know that the current diagnostic classification in the DSM or ICD may not reflect the underlying etiology of these disorders, as suggested by the heterogeneity of clinical presentations within a diagnostic category, but also knowing the large overlap that exists in clinical symptoms, in cognitive deficits, or genetic risk factors across diagnosis, as well as the high comorbidity rates among psychiatric disorders. So to have a better idea of how porous psychiatric labels are, this figure shows how much having any of these disorders on the left increase your chance of having any of the disorders on the right. And this is when considering large categories such as developmental disorders, which encompass many diagnostic subcategories from autism spectrum disorder to intellectual disability disorder. So you can imagine that the comorbidity between disorders among these categories is even more important. So in this context, unsupervised learning can help to uncover some of the common underlying neurobiological processes that cross diagnostic boundaries. Now I'm going to go into one specific unsupervised approach called partial least squares, or PLS. PLS is a powerful unsupervised technique that finds how to optimally relate two matrices. And before going into the details, just be aware that PLS has many variants, which depend on the type of data that you're trying to relate. For example, imaging and behavioral measures, or group labels, or task conditions. There's also PLS regression, which is a little different, as it tries to predict the matrix Y using the X matrix. And in this talk, I'll be explaining behavior PLS, which relates imaging to behavioral data. So imagine you have a set of subjects. For each subject, you have imaging data, for example, a functional connectivity matrix, and behavioral data, for example, symptoms or cognitive scores. And the goal of PLS is to find the shared information between two modalities. So here, PLS will aim to find imaging patterns that are related to patterns in the behavioral data. And it works by finding low-dimensional latent variables that show maximal covariance. To obtain these latent variables, PLS finds weighted pairs of vectors, which are matrices V and U. And each column in V and U corresponds to a different component that relates imaging to behavior in a different way. The matrix V is composed of weights for each imaging variable and each component, and the matrix U contains weights for each behavior and each component. And these two matrices are called saliences in the PLS terminology, and are similar to the coefficients that you get in principal component analysis. And when you project your imaging and your behavioral data on the saliences, you obtain what we call latent variables, which are essentially subject-specific imaging scores and behavior scores for each component. And those are similar to the principal scores in principal component analysis. So let's say you have your imaging data in X, where each row is a different subject and each column a different connectivity value. And your behavioral data is in matrix Y, where rows are the same subjects as in X, with a behavioral measure in each column. After we normalize both X and Y, we compute a cross-covariance matrix between the two. Then we decompose this covariance matrix using singular value decomposition into three low-dimensional matrices, U, S, and V. U contains the behavioral saliences, V contains the imaging saliences, which here are resting state functional connectivity saliences, and S is a diagonal matrix containing the singular values. And finally, we project the original data X and Y on the saliences to obtain LX and LY, which are the latent variables, containing the subject imaging scores and behavior scores for each component, showing how much each subject expresses the imaging and behavioral patterns of each component. Singular value decomposition is central to PLS, and it determines a few things about the components that we find. First, the rank of the covariance matrix R determines the number of components. That will be the smallest dimension between the number of subjects, behaviors, and connections. The components are ordered by effect size or magnitude, which is expressed by the singular values in matrix S. And the amount of covariance explained by each component is the ratio of the square of the singular value of a particular component to the sum of all squared singular values in this matrix S. And finally, components are orthogonal, so that each component explains a different part of the covariance between the imaging and behavioral data. So in other words, each component represents a distinct association between imaging and behavior. So what analysis does PLS entail? Each of our analyses will answer a different question, with the first question being, is there a relationship between my imaging and behavioral data? So for this, we compute PLS between your two data matrices. Next, we want to test and interpret these components, first by assessing which components are significant, using permutation tests. Second, by testing which variables drive these components and how robust they are, which can be assessed with bootstrapping. And finally, you might want to check whether these components are generalizable to unseen data using cross-validation. And I'll go into each of these steps one by one. So first, we want to test which of our components are significant. We use permutation testing, whereby we permute the rows of the behavioral matrix Y. Then we recompute the cross-covariance matrix and decompose it into U, S, and V. As I mentioned before, the singular values in the matrix S express the magnitude of the association between imaging and behavior. And we use this matrix S to build a distribution of singular values under the null hypothesis. And this allows us to test the significance of each component by dividing the number of times the null hypothesis is true by the number of permutations. And here we added 1 to both the numerator and denominator to avoid having a p-value of 0. Next, we're interested in interpreting these components, so we want to know which variables drive or characterize these components. And this is often assessed in terms of loadings, which can either be the saliences or the structural coefficients, which are the correlations between the original variables and latent variables. Either way, we will have a set of imaging loadings for each component and a set of behavioral loadings for each component. And both saliences and structural coefficients are used in the literature. But if you have multi-collinearity in your data matrices, you might want to use structural coefficients because saliences might be sensitive to it. But keep in mind, though, that saliences and structural coefficients will usually be highly correlated. Next, you want to find out whether your loadings are robust, irrespective of the sample. For this, we use bootstrap resampling, and I'll demonstrate this over the saliences, but it's also possible to run bootstrapping over the structural coefficients, as I'll show you in the example later. So we sample both the imaging and the behavioral data. Then we recompute the cross-covariance matrix and decompose it. And after we do this a number of times, we can compute a standard error for each imaging and behavioral loadings across all samples. Then we can compute what we call bootstrap ratios, which are the original loadings divided by the standard error. And we consider robust the loadings that are high with a low standard error. An important question is whether our components are generalizable to unseen data. Indeed, as other unsupervised techniques, PLS tends to overfit. For this, we use cross-validation. We start by separating the imaging and the behavioral matrix into a training and a testing set. Then we recompute a cross-covariance matrix using the training data, which we decompose to obtain the saliences. And then we project the test data over the saliences of the training data in order to obtain new latent variables. And finally, to test the association between behavior and imaging in the unseen data, we compute correlations between these new latent variables. I'll now demonstrate how PLS works using an example from some data that we published last year using the UCLA Consortium for Neuropsychiatric Phenomics dataset, which includes data from individuals with various psychiatric disorders as well as healthy controls. So in our PLS analysis, on the imaging side, we have time series from 400 cortical ROIs from the Schaefer Atlas, as well as 19 subcortical ROIs. We computed Pearson's correlations between all pairs of brain regions. Then we vectorized the correlation matrices and stored the data of all subjects into this matrix X. On the behavior side, we have 54 measures of clinical symptoms, cognitive scores, and personality scores, which are stored in matrix Y. Using permutation testing, we found 3 significant components. And these plots show the correlation between the latent variables, and each dot represents a different subject on each of these significant components. And you can see the null distribution of the singular values obtained with permutation testing on the top left side of each scatter plot, along with the p-value obtained for each component. And I'm going to go into the first component in more details. So if we take a look at the loadings, on the right here are the top 20 behavioral loadings, which are all robustly associated with the first component. By looking at these measures, we can infer that this component is characterized by clinical symptoms, such as mood symptoms, anxiety, depression, or ADHD symptoms. And since the symptoms are not very specific, we interpreted this component as being a general psychopathology dimension. So if a subject has a high behavior score on this component, it means that this subject has greater psychopathology. On the imaging side, we have the resting state functional connectivity loadings that are associated with greater psychopathology, including decreased functional connectivity within the somatomotor network and increased connectivity between the dorsal attention, somatomotor, and visual network on one side, and the default control salience and subcortical networks on the other side. We use bootstrapping to assess the robustness of these loadings. Using 500 samples with replacement, we estimated the standard deviation for loadings and computed bootstrap ratios by dividing each loading by its standard deviation across all the samples. Because we had over 80,000 connections, to limit the number of comparisons, we decided to average the bootstrap ratios within and between networks. And these bootstrap ratios are similar to z-scores, which can then be converted to p-values and FDR corrected. And now on the right side, we only see the loadings that were found to be robust. Finally, we used five-fold cross-validation to test the generalizability of our model. And we found that the three components were still significant, although the correlations were much lower. So in this last part of my talk, I'll explain how PLS compares to other unsupervised techniques such as PCA or CCA. One unsupervised technique that has many similarities with PLS is principal component analysis. Indeed, PCA creates a set of low-dimensional variables called principal components, which are linear combinations of the original data from X. PCA is also based on singular value decomposition, which decomposes the data in uncorrelated principal components that capture unique, non-overlapping portions of the variance. And these components are ordered by the amount of variance they explain. Basically, PCA applies singular value decomposition on the covariance between X and X, and the component coefficients are in matrix V, while the component scores are obtained by projecting the original data on the coefficients, just like latent variables in PLS. The second technique that I'm going to explain briefly is canonical correlation analysis, which you might have heard of and might be wondering how it's different from PLS. Conceptually, the two techniques are very similar. Just like the latent variables in PLS, CCA aims to create canonical variates, which are linear combinations of the original variables X and Y. And CCA aims to maximize the correlation between these canonical variates, while PLS maximizes the covariance between the latent variables. But mathematically, there's an extra step in CCA. Before computing the cross-correlation matrix, X and Y are first adjusted for within set correlations. However, when you have more variables than you have samples, which is often the case when you deal with imaging data, you can't factorize your imaging matrix X because it's rank deficient. Therefore, dimensionality reduction is usually applied before computing CCA. And you can see on the right here that the correlation matrix of Y and X is adjusted for correlations within the matrices Y and X before the decomposition. And the coefficients or saliences are called canonical variates in CCA, and the latent variables or principal scores are called canonical scores. So if you're interested in using PLS, there are several toolboxes that are available. We have developed a MATLAB PLS-based toolbox called MyPLS with Daniela Zoller, where you can use behavior PLS on different sorts of imaging data, either one-dimensional, such as graph metrics, two-dimensional, like correlation matrix, or three-dimensional, like voxel-based data. And we have a poster showing what you can do with our toolbox if you want to check it out. There's another MATLAB-based toolbox developed by the Rotman-Bakers Institute, which features different variants of PLS with 3D and 4D imaging data. And finally, if you're more comfortable with Python, Ross Markello has developed a Python-based toolbox that allows you to do behavior PLS, mean center PLS, and PLS regression. And I'll leave you with some references for PLS. First, this tutorial by Krishnan and colleagues, which is very accessible, and the seminal paper by Randy McIntosh about PLS applied to neuroimaging data, and also these two papers about other multivariate methods for analyzing neuroimaging data. And finally, I'd like to thank my PhD supervisor, Dimitri Mandeville, who taught me everything I know about PLS, as well as my current supervisor, Thomas Yeo, as well as our lab sponsors, and thank you for your attention.
All right, awesome, well done here.